everybody. Today we're going to talk about section 7.4, which is integration using partial fractions. So our objectives is to integrate any rational function f of x equals p of x over q of x such that p and q are polynomials using the partial fractions method. So first let's see some examples to understand the idea of the partial fraction method. Okay, for example, if I ask you to evaluate the integral which is 2 over x squared minus 1 dx. Okay, it is from the first sight is not easy to calculate it. Yeah, maybe you say, okay, using the hyperbolic functions, you can say that this is like the tangent inverse or the cotangent inverse. Okay, but still we have another method, which is we can say that 2 over x squared minus 1 can be written as 1 over x minus 1 minus 1 over x plus 1. And so to integrate this one it's easy to integrate 1 over x minus 1 and 1 over x plus 1. For example, so the integration of 2 over x squared minus 1 dx equals the integration of 1 over x minus 1 dx minus the integration of 1 over x plus 1 dx, which is ln x minus 1 minus ln x plus 1 plus constant. Okay, so this was the first example. Let's see the second one. So the second one is still not hard. If I ask you to calculate this one, which is the integration of x of this rational function, which is x plus 5 over x squared plus x minus 2 with respect to x. Yes, now still you can do some tricks like completing the square and then use the appropriate inverse functions for the trig functions or the hyperbolic functions, but still we have a much easier method here. So we can rewrite this fraction as the sum of two easier fractions, which is 2 over x minus 1 minus 1 over x plus 2. So to integrate f of x, it's the same as integration this sum. So I will be the integration of 2 over x minus 1 with respect to x minus the integration of 1 over x plus 2 dx, which is 2 times ln absolute value x minus 1 minus ln absolute value of x plus 2 plus constant. Okay, we still have another example. So, example, if you want to integrate x cubed plus x over x minus 1. Okay, you can note that the degree of the numerator is 3 and the degree of the denominator is 1. Okay, so these kind of rational functions, which is p of x over q of x, such that the degree of b is greater than or equal degree of q. This fraction is called improper fraction. And actually, you can use the long division to simplify this function. So using the long division, you can rewrite f of x as for example, s of x plus r of x over q of x. Okay, where the degree of r of x is less than the degree of q of x. Okay, and this point will make our problem much easier. Let's see that in our example. Okay, so here you have x cubed plus x over x minus 1. So the degree of the numerator is 3 and the degree of the denominator is 1. Okay, so let's apply the long division. So here you have x cubed plus x, and here you have x minus 1. So if you divide x cubed by x, so here you will get x squared, and then you multiply. So x squared times x, which is x cubed, and then x cubed minus x times 1, so you have minus x squared. And then you subtract. So you change the sign. So this will be 0, and here negative. You will have x squared and then plus x. Okay. And then you divide x squared by x, so here you will have plus x, and then multiply x by x minus 1, so you will have x squared minus x, and then again you change the sign, you subtract, so you'll have 0, and here you'll have 2x, and finally, okay, 2x over x, you'll have plus 2, so 2 times x minus 1 will be 2x minus 2, and then again you change the sign, so you will have 0, and here the remainder will be 2. Okay, so this way we can, using this information from the long division, you can write f of x cubed plus x over x minus 1 as the quotient, which is x squared plus x plus 2, and then plus the remainder, which is 2 over x minus 1. So if you want to integrate x cubed plus x over x minus 1, it's much easier to integrate the quotient, which is x squared plus x plus 2 with respect to x, and 2 over x minus 1 with respect to x. And the integration easily will be x cubed over 3 plus x squared over 2 plus 2x plus 2 then absolute value of x minus 1 plus c. So using the trick of the long division, we get a much easier integral. Okay, and actually this is a necessary condition to apply the partial fraction method. So the partial fraction method will be applied to the proper fractions. What do we mean by the proper fractions? Which is the fractions such that the degree of the numerator is less than, not equal, strictly less than the degree of the denominator. Okay. So now we're ready to see the partial fraction method. So we're ready to see the partial fractions method. Okay, so given a rational function f of x, which is p of x over q of x, such that the degree of p is less than the degree of q. Otherwise, you have to apply the long division such that you will get a quotient and a proper rational function. Okay, as we saw in the last example. Okay, so our steps. So the first one is to factorize the denominator, which is q of x, as far as possible. Okay, so from the theory we know that any polynomial, this can be proved, that any polynomial can be factorized into a product of linear factors of the form ax plus b and irreducible quadratic factors of the form ax squared plus bx plus c. And actually reducible, which is equivalent to this condition, which is b squared minus 4ac is negative. So this cannot be factorized over r. Okay, so we're talking about real coefficients. So a and b and c are real coefficients. Okay, so this is the first step. The second step, we will make it as a cases, but formally we can say that we can express f of x, which is p of x over q of x, as a sum of partial fractions of the form a over ax plus b power I, or ax plus b over ax squared plus bx plus c whole to the power j. Okay, actually this step we will divide it into 4 cases, and we will say that in detail, and we will illustrate it using some examples. Okay, so our first example, which is to evaluate this integral, which is x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x with respect to x. Okay, so the first thing is to check our condition. So the degree of the numerator is 2 and the degree of the denominator is 3. So 2 is less than 3. So we can apply the partial fraction method. So there is no need to the long division here. Okay, so the first step, solution. The first step is to factorize the denominator. So cube x here equals 2x cubed plus 3x squared minus 2x. So it's easy to see that we can take x as a common factor. So here you have 2x squared plus 3x minus 2, and this can be factorized easily. This can be factorized easily into product of 2 linear factors, which is 2x minus 1 times x plus 2. Now we're done with the first step. Okay, so now we factorize q of x into linear factors, and actually this is the first case which you have your q of x, your denominator, is factorized into linear factors. All of them are distinct. Okay, so all of them will be with power 1. So in this case, so which is the second step, you have to write your fraction, your rational function, which is the same as x squared plus 2x minus 1 over x times 2x minus 1 times x plus 2, as a sum of 3 fractions, 3 partial fractions. You'll have 3 partial fractions. The first one will be corresponding to the first linear factors, the first linear factor, which is x, and the second one will correspond, the second one will correspond to the second one, and the third one will correspond to the third one. Okay, so, and here you have, since this is linear, you have to put in the numerator, you have to put just a constant. Okay, and actually now as an integration, if you want to integrate this function, it's easy to integrate these 3 functions. Okay, so if I want to calculate I, so I will be the integration of a over x with respect to x plus the integration of b over 2x minus 1 with respect to x plus the integration of c over x plus 2 dx. So I will be a times ln absolute value of x plus b over 2 ln 2x minus 1 plus c times, okay, plus c times then x plus 2 plus constant. Okay? So the problem of the integration is done, but it remains for us to calculate what's a and b and c. And actually we're going to do that in two ways. So it remains for us to calculate these constants, which is a and b and c, and we're going to do that in two ways. So method 1 and method 2. The first method by comparing the coefficients, and the second one by substituting with instead of x by some real values. And most of the time this method is much easier the first one. Okay, let's see how to calculate this a and b and c. Okay, so common denominator, which should be the same as this one. So for this case, since our factors, all of them are linear, so it doesn't matter, so we will multiply all of them. So we'll have x times 2x minus 1 times x plus 2, and then here you will have, in the numerator you will have a times 2x minus 1 times x plus 2, and then you'll have plus b times x plus 2 plus c times x times 2x minus 1. Okay, so here the left hand side was x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. So we can cancel this with this because they are the same. So you will have x squared plus 2x minus 1 equals a times 2x minus 1 times x plus 2 plus b times x plus 2 plus c times x times 2x minus 1. And here we can begin with the first method. So which is by comparing the coefficient. So method 1. So we can collect the coefficient of x squared and x and the free term on the right hand side. So you will have x squared plus 2x plus 1, which equals 2a plus b plus 2c times x squared plus 3a plus 2b minus c times x minus 2a. And by comparing the coefficients, we will have minus 2a equals 1. Or even before we compare the coefficient, how did we get that? So actually, when you multiply them, so the first term will be 2x times x, which is 2x squared. So and then it will multiply it by a. So in the coefficient of x squared, you should have 2a. And also from here, you will have bx times x, so you will have bx squared, so you should have b. And again, cx times 2x, which is 2c times x squared, so you have to have 2c. And also with respect to x, you have the coefficient of x here will be, here you will have negative x and 4x, so it's a 3x times a, so you will have 3a. Okay, and here you will have 2bx, so you should have 2b, and here you will have negative cx, so you should have negative c. Okay, and the free term here, we don't have a free term because it's multiplied by x and multiplied by x here also. But here you will have negative 1 times 2, which is negative 2 times a, so you will have negative 2a. So by comparing the coefficient, we will have the coefficient of x squared, which is 2a plus b plus 2c equals 1, and the coefficient of x, which is 3a plus 2b minus c, which is 2, and negative 2a equal 1. So from here you will have a equals negative half, and then maybe you substitute here and here, so you will get this system. So if you multiply, if you substitute by negative half, so you will have negative 1. So the first equation will be b plus 2c equals 2, and the second one will be 2b minus c equals, so this is negative 3 over 2, and then you will get it on the other side, 3 over 2, so 2 plus 3 over 2, so 3.5, so it's 7 over 2. Okay, and easily you can solve these two equations simultaneously, and you will get b equals 1 over 5 and c equals negative 1 over 10. And in this way we could get the values of a and b and c. So we done of this example using the first method. Let's see the second one, which is very easy also. Okay, so before we begin, we have in the first and second method we have some common steps. So our fraction is x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x, which equals a over x plus b over 2x minus 1 plus c over x plus 2. Okay, so we can make a now let's see the second method. So method 2, you can call it the substitution method. Okay, here we will substitute by real numbers, and sometimes, or most of the times, we will substitute by the zeros of the denominator. Let's see how can we do that. So we reach to this equation, which is x squared plus 2x minus 1 equals a times 2x minus 1 times x plus 2 plus b times x plus 2 plus c times x times 2x minus 1. Okay, so the zeros of the denominator, our partial fraction expression was a over x plus b over 2x minus 1 plus c over x plus 2. So we're going to substitute by the zeros of the denominator. Okay, so the first one is, which is x equals 0. So if you substitute by x equals 0, the left hand side will be negative 1, and the right hand side will be a times negative 1 times 2 plus 0 because of this x, and plus 0 because of this x. Okay, so in this way a equals half, and this is the first constant. And if we substitute by the second zero divisor here, which is x equal half, so you will have in the right hand side you will have half squared plus 2 times half minus 1 equals, okay, here 2x minus 1 will give us 0 plus b times half plus 2, and then plus c times half times 0, so all of this will be 0. So b equals 1 over 5. Okay, the last substitution here for x equal negative 2. Okay, so if you substitute with x equal negative 2, so we'll have 4 plus 2 times negative 2 minus 1. This was the left hand side, and the right hand side here you have x plus 2, so when you substitute by negative 2, so this is 0, and again here x plus 2, so this will be also 0 plus c times negative 2 times negative 4 minus 1, so c equals negative 1 over 10. Okay, so in this way was the these values were the zeros, or this, and actually these values are the values of the zeros of the denominator of our rational function. So, and these values gives us directly the values of the constants. Okay. Now let's erase and let's conclude the first case. Case 1. In this case, cube x splits completely into linear factors such that all of these linear factors are different. Okay, so in this way, so cube x equals a1x plus p1 times a2x plus p2 up to akx plus pk, such that all of those are different. So we can write it as this is cube x is a product of distinct linear factors. Okay, so we know that f of x equals cube x over cube x. So our partial fraction decomposition is a1 over a1x plus p1 plus p1 over a2x plus p2 up to, sorry, let's call this a2, up to ak over akx plus pk. Okay, so when all of them are not repeated, so each one of them will share one partial fraction. Each one of those we call it partial fraction. Okay, so now what about if one of our linear factors is repeated? Okay, actually this is our second case. So case 2, and we will have that cube x is splits completely into linear factors, but one of them or some of them will be repeated. So for example, let's consider that the first one is repeated r times, and the other linear factors are not repeated. Okay, so cube x will have this form. Okay, so actually as we see in the first case, that each one of the linear factors which is not repeated will share one partial fraction. Okay, but what about this one which is repeated r times? So this will so here we will have f of x, which is cube x over cube x. So this is repeated r times, so it will share r partial fractions as follows. This would be a1x plus p1. In the numerator we write a constant, and then here we'll have a1x plus p1 squared, and here we'll have a constant up to ar over a1x plus p1 all to the power r. Okay, and the other linear factors will share just one partial fraction. So we'll have a2x plus p2, and here we'll have a constant, for example, let's call it p2, up to akx plus pk, and in the numerator we will have bk. So each one which is raised to the power 1, so which is not repeated, will share just one linear just one partial fraction. Okay, and the one which is occurs r times in the factorization of cube x will share r partial fractions. Let's see an example to understand it. So example, okay. Okay, if you have this rational function, which is x cubed minus x plus 1 over x squared times x minus 1 all cubed. So the first condition is satisfied, which is the degree of the numerator is 3 and the degree of the denominator is 5, because this will be x cubed times x squared. So to get the partial fraction decomposition, so here you will have here this x is actually two linear factors which is repeated, a linear factor which is repeated, and here it's like x minus 1 times x minus 1 times x minus 1. So here you will have this linear factor will share two partial fractions, which is the first one will be a over x, or a1 over x, and the second one will be a2 over x squared. Okay, and this one will share, since it's repeated 3 times, so it will share 3 partial fractions. So it will be x minus 1 and x minus 1 squared and x minus 1 cubed. So x minus 1 we will lock inside the bracket. So this is linear, so we will write a constant again inside the bracket. So this is linear, which is x minus 1. So we will write a constant again, a5. So this will be the partial fraction decomposition of this rational function. Okay, so now let's see another example. Evaluate the integral of 4x over x cubed minus x squared minus x plus 1 with respect to x. So again, the first condition is satisfied. The degree of the numerator is 1 and the degree of the denominator is 3, so we can apply the partial fraction method. Okay, so the solution, so let's say cube x equals x cubed minus x squared minus x plus 1. You can easily verify that cube 1 is 0, so x minus 1 is a factor of cube x. Okay, so if you apply the long division, so cube x will be x minus 1 times x squared minus 1, and actually this can be factorized easily. It will be x minus 1 times x minus 1 times x plus 1. So cube x splits into x minus 1 squared times x plus 1. So this is the factorization of cube x. Okay, so this was our first step. Second step is and actually in this step we can see that we have a linear factor which is repeated. So we are in the second case. So it's split into linear factors and one of them is repeated. So if the partial fraction decomposition of this rational function is a over x minus 1 plus b over x minus 1 squared, because this is repeated 2 times, and c over x plus 1. Okay, actually this equation can be written as 4x over x cubed minus x squared minus x plus 1, and here on the right hand side we'll make a common denominator. So here you will have x minus 1 squared times x plus 1. Okay, so and then you will have a times x plus 1 times x minus 1 plus b times x plus 1 plus c times x minus 1 square. Okay, so now you can cancel these two denominators together, so you will get 4x equals a times these two will be x squared minus 1 plus b times x plus 1 plus c times x minus 1 squared. And here you can find a and b and c using our two methods. So let's begin with the first one, which is we will compare the coefficients after simplifying the right hand side. So method 1. So we'll have here 4x, and the right hand side, if you get the coefficient of x squared, so here you will have a, because a will multiply it here, and here you will have c. So you will have a plus c times x squared, and then plus the coefficient of x here, there is no a, and here you will have b, and here you will have negative 2c times x, and for the free term you will have here you will have negative a plus b plus c. Okay, so by comparing the coefficients you will get these three equations. The first one is a plus c equals 0, so a equals negative c. The second one is b minus 2c equals 4, and the third one is negative a plus b plus c equals 0. Okay, so if you substitute by the value of a in the third one, and then you solve these two equations simultaneously, you will get that b equals 2 and c equals negative 1. Since a equals negative c, so you will have that a equals 1. So now we calculated the values of a and b and c using the first method. Let's see how can we calculate them using the second one. So method 2, substitution method, because actually we're going to substitute by the values of x, which will give you 0 in the denominator. Okay, so let's see. So now we know that the zeros of the denominators are 1 and negative 1. So if you substitute by x equal 1, here exactly in this equation, if you substitute by x equal 1, so the right hand side will be 4, and the left hand side here, this will be 0, and this will be 2b, and this will be 0. So you will have 0 plus 2b plus 0. So you can find that b equals 2. Okay, which is the same as this one. And if you substitute by the other 0 divisor, so which is negative 1, okay, as you can see here from this factor. So if you substitute by x equal negative 1, so here the left hand side will be negative 4, and the right hand side, if x equal negative 1, where yes, so this again will be 0, because negative 1 squared is 1 minus 1, which is 0, and this will be 0, and the last one will be 4c. So it will be 0 plus 4c. So you can see that c equals negative 1, which is the same as the value that we get by the first method. So, but now we don't have other 0 divisors. So what can we do? So actually, this relation or this identity is true for every x. So you can choose any x. You can choose a special value of x which makes these equations pretty simple. So actually, if you choose x equals 0, so the left hand side will be 0, and the right hand side will be negative a, and here you will have plus b, but we know that b is 2. Plus C, but also we know that C is -1, so easily you can see that A equals 1, which is the same as the value that we get in the first method. Okay, so we get A and B and C. So let's see how to calculate the integral. Okay, so I will be the integration of 1 over x minus 1 with respect to x plus the integration of 2 over x minus 1 squared with respect to x plus the integration of where is C? Yes, -1 over x plus 1 dx. So the first one and the third one is very easy to integrate, and the second one also actually. So I will be then absolute value of x minus 1 plus 2 times x minus 1 power -1 over -1 plus or minus, we can get this negative outside, so then the absolute value of x plus 1 plus constant. Okay, so in this way we're done with this example. Let's go for the third case. As we say that in this case that the cube x will have a quadratic irreducible quadratic factor. So for example, let's say that cube x will be like ax squared plus bx plus c, which is in this case raised to the power 1, and maybe let's call it a1 b1 c1, and maybe you will have another or maybe not another quadratic expression, quadratic factor, which is a2x plus b2 a2x squared plus b2x plus c2 times other linear factors, or maybe you don't have, so it doesn't matter. So let's write it as in the most general form. So we will have like a3x plus b3, okay, maybe let's call it to the power r, times a4x plus b4 up to a kx plus bk. The partial fraction, so the partial fraction decomposition of p of f of x, which is p of x over q of x, will be, so again each factor which is raised to the power 1 will share by one partial fraction. Okay, so here you will have a1x squared plus b1x plus c1. Okay, and this is all to the power 1. Yes, so here in the numerator, in this case in the numerator, you have to write ax plus b, a linear factor. Since this is a quadratic, so you have to write in the numerator, you have to write a linear expression. So let's call it a1 b1. Okay, plus again for the second one, so here you have a2x squared plus b2x plus c2, and since it's linear, so it will share with only one partial fraction. And in the numerator, again, if you look inside the brackets, you will find a quadratic expression. So here you have to write a linear one, so a2x plus b2, and then with respect to these factors, will be done as in case 1 and 2. Okay, so let's see an example to understand this situation. So here again, so consider this rational function. So x cubed plus x plus 1 over x squared times x plus 1, let's say cubed, times x squared plus x plus 1. Okay, I forget to say something, that this factor is irreducible and this factor is irreducible, so I cannot factorize this into two linear factors. And actually the word irreducible here, it's equivalent to say that b1 square minus 4a1c is negative, and here's the same, b2 square minus 4a2c2 is negative. Okay, so here we can find that since this is a quadratic factor which is irreducible. So in this example, we want to find the partial fraction decomposition of this rational function. Okay, so here this is a linear factor which is x, and it's repeated 2 times. So you will have it will share 2 partial fractions, something over x and something over x squared. So here you will have a and here you will have b. Why b? Why not bx plus c? Because this is x all squared. Okay, so we look inside the bracket, so you will find this is linear. So you have to write something which is less than degree here by 1. So you have to write something which is constant. Okay, so plus the second one is x plus 1 all cubed. So this will share 3 partial fractions. So the first one x plus 1, the second one x plus 1 squared, and the third one is x plus 1 cubed. And again, this is linear, so we will write a constant. So we will have like c, and here d, and here e. So what about this quadratic factor here? So you will have x squared plus x plus 1. So since this is power 1, so again we'll share by 1 one partial fraction. So, okay, so and since this is quadratic, so you have to write a linear expression in the numerator. So you will have like fx plus g. Okay, so in this way we wrote the partial fraction decomposition of this rational function. Okay, now let's go for another example. Okay, so example, we want to evaluate the following integral, which is 2x squared minus x plus 4 over x cubed plus 4x with respect to x. Let's call it I. So the degree of the numerator is 2, and the degree of the denominator is 3. So we can apply the partial fraction method. So we begin with the first step, that we have to factorize our denominator, which is cube x, as far as possible. So here we can take x as a common factor, so you will have x times x squared plus 4, and actually this is irreducible, because if you apply the expression for b squared minus 4ac, you will find that b squared is negative. Okay, because b squared minus 4ac will be negative, because here b is 0, b is the coefficient of x, and a and c are 1 and 4, so this will give you a negative value. So we know that this factor is irreducible. So here our cube x has an irreducible quadratic factor, so we are in case 3. So the second step now is to rewrite the decomposition, the partial fraction decomposition of this function, of this rational function. So you will have x cubed plus 4x. So you will have, here you have 2 factors. The first one is x, which is linear and not repeated. So we'll write x, and here you will have a constant plus the second factor, which is not repeated also. So it will be x squared plus 4. And since this is quadratic expression, so you will have bx plus c. So the second step here will be that we are going to make a common denominator. So you will have 2x squared minus x plus 4 over x cubed plus 4x equals here our denominator will be the same as the original one, which is x times x squared plus 4, and the numerator here will be a times x squared plus 4 plus bx plus c times x, and then you can cancel these two factors because they are the same, so you get our important equation. That's 2x squared minus x plus 4 equals a times x squared plus 4 plus bx squared plus cx. Okay, and here you have, as usual, we have two methods. So let's solve using the first one. We have actually these two methods will allow us to calculate a and b and c. So the first one is to get a and b and c by comparing the coefficients. Right? So if you rewrite it, so you will have 2x squared minus x plus 4 equals a plus b times x squared plus cx plus 4a. So if you compare the coefficients now, so you will have a plus b equals 2, and you will have c equals -1 and 4a equals 4. So from here a equals to 1. So if a is 1, so from the first equation that b is 1. So we get a and b and c. So you can do the same thing using the second method, that we call it the substitution method. Okay, so usually we substitute by the zero divisor. So the zero divisor here is x equals 0, and we don't know a real number. When we square it, we get -4. Okay, so we have only one zero divisor here, which is x equal 0. So if x equals 0, if I substitute in this equation, so you will get 4 equals, if x equals 0, so this will be 0 and this will be 0. 4 equals 4a. So from here a equals 1, and you can choose any other x, any other values, because actually this equation is true for every x. Okay, so if you choose x equal 1, so here the left hand side will be 2 minus 1 plus 4, and the right hand side will be we know now a is 1, so it will be 5 plus b plus c. So the first equation is b plus c equals, here you have 2 minus 1, which is 1, so b plus c equals to 0, which means that b equals to -c. Okay, so we can continue using another value. Okay, so if you choose, for example, here we choose, we had to choose in x equal 1. So if you choose x equal -1, what you're going to get? So you will get, again, we substitute in this equation, so you will get -2 plus 1 plus 4 equals 5a. Okay, and a is 1, so we will get 5 plus b minus c. So again, so this will give you that b minus c equals, this is 5, so b minus c equals 2, but we know that b equals -c. So since b equals -c, you can get that 2b equals 2, so b equals 1, and again, so since p equal negative c, so c equals negative 1, which is the same as the values that we get in the using the first method. So since now we know the value of a and b and c, so let's substitute here. So this is our rational function will be a over x, and we calculate a is 1, and plus bx plus c over x squared plus 4, and b is 1 and c is negative 1. So now this is our partial fraction decomposition, okay, of this rational function, and now we want to integrate this, okay, which is easy. Let's see it. We reach to this step, which is 2x squared minus x plus 4 over x cubed plus 4x has the following partial fraction decomposition, which is 1 over x plus x minus 1 over x squared plus 4. So if you want to integrate this one, if you want to integrate this with respect to x, you can integrate this with respect to x plus the integration of this with respect to x, which equals the integration of 1 over x with respect to x plus the integration of x over x squared plus 4 with respect to x minus the integration of 1 over 4 plus x squared plus 4 plus x squared with respect to x. Okay, so the first one is easy, so this is just len absolute value of x, and the second one here you need 2.5 such that the numerator becomes the differentiation of the denominator, so you will have half times len absolute value of the denominator, and actually this is can be integrated easily because we know that the integration of 1 over a squared plus x squared with respect to x is 1 over a times tan inverse of x over a plus constant. So this is will be half times tan inverse of x over 2, where this 2 is just the square root of 4 plus constant. Okay, so actually so we're done with this example. Actually I had chosen this example a little bit easy because the partial fraction decomposition gives us x minus 1 over x squared plus 4, which is easy to integrate. But actually what will happen if our partial fraction decomposition contains something like that? Ax plus b over ax squared plus bx plus c. How can we integrate such rational function? So let's see an example to see how can we deal with this kind of integrals, which is not hard, but let's see an example to see how can we deal with it. So example, we want to evaluate this integral, which is x minus 1 over 4x squared minus 4x plus 3 with respect to x. Okay, so here now this is a quadratic expression, so which is irreducible because b squared minus 4ac is negative. So here we cannot use the partial fraction method, and we want to integrate this rational function. Okay, so actually we can use our usual trick, which is completing the square. So 4x squared minus 4x plus 3 can be written as 2x minus 1 whole squared minus 1 plus 3. So this can be written as 2x minus 1 whole squared plus 2. Okay, so our integral becomes x minus 1 over 2x minus 1 squared plus 2 with respect to x. And then if we use this substitution, which is u equals 2x minus 1, so du will be 2 dx, and x will be u plus 1 over 2. We will have u, the integration of u plus 1 over 2 minus 1, okay, which is x minus 1, over u squared plus 2 times dx, and from here we can find that dx is half du. So our integral becomes, if we make a common denominator here, so we will have u plus 1 minus 2, and then here you will have half and half, so you will have 1 over 4. Half times half will be 1 over 4 over u squared plus 2 du. So u plus 1 minus 2, which is the same as u minus 1. And again, you can split this into two sums, into two fractions. So we'll have 1 over 4, the integral of u over u squared plus 2 with respect to u, minus 1 over 4 integral of u squared plus 2 with respect to u. So it will be 1 over 4, and here you need 2 and half, such that the numerator becomes a differentiation of the denominator. So you will have 1 over 8 ln u squared plus 2 minus 1 over 4 times the square root of a squared, the square root of 2, which is 1 over square root of 2, tan inverse of u over square root of 2 plus constant. So, and then you have to replace u by its value, which is 2x minus 1, so you will get 1 over 8 ln 2x minus 1 squared plus 2 minus 1 over 4 square root of 2 tan inverse of 2x minus 1 over square root of 2 plus constant. So let's summarize how can we solve this kind of integral, which is ax is the integral of ax plus b over ax squared plus bx plus c with respect to x. Okay, so the first thing, you have to complete the square. With the denominator. And the second thing is to use an appropriate substitution. And if you apply these two steps, you will get an integral like that. That will be c times u plus d over u squared over plus a squared with respect to u, which can be split into two integrals like that: c times u over u squared plus a squared with respect to u plus d times 1 over u squared plus a squared with respect to u, which is easy to integrate. So the first one will be c over 2 times ln u squared plus a squared, because the differentiation of u squared plus a squared is 2u. So if you multiply by 2 and divide by 2, so the numerator will be the differentiation of the denominator, so the integration will be ln absolute value of the denominator, plus second one is d times, this is the usual integration, so you will have 1 over a times tan inverse of u over a plus constant. So this is the general way to compute such integral. Okay, now so we saw how to deal with the quadratic factor if it's not repeated. What if it's repeated now? So what if cube x, which will be case number 4, the fourth case, if cube x contains a factor like that, ax squared plus bx plus c all to the power r. So a quadratic factor which is not which is irreducible. So you will have b squared minus 4ac is negative, and actually it's repeated. So what should we do? So times some other factors. This quadratic factor will share our partial fractions as in the repeated linear factors. So this one will share the following partial fractions. So we'll have here ax squared plus bx plus c plus ax squared plus bx plus c squared, and so on up to ax squared plus bx plus c all to the power r. And in the numerator, as usual, this is quadratic, so you will write, for example, a1x plus b1, and again, I'm looking inside the bracket, so this is quadratic, so a2x plus b, and again here arx plus br, so this is b2. Okay, so let's see an example to understand the last case. Example, if I want to calculate the partial fraction decomposition of such a rational function, so we'll have x cubed plus x minus 5 over x times x minus 1 times x squared plus 1 cubed times x squared plus 1, plus x plus 1. Okay, so this is not hard, but we will have many partial fractions. So the first one, so let's look to the linear factors. So no one is repeated, so you'll have x, one partial fraction with us for x, and another one corresponding to x minus 1, and here for this quadratic which is not repeated, which is x squared plus x plus 1, you'll have just 1, or x squared plus x plus 1. Okay, let's write here this is linear, so we will write a constant, and again this is linear, so we will write a constant, and again not again. So, and here this is quadratic, so you have to write linear, so cx plus d. Okay, and then this is our repeated quadratic factor, so this will share 3 partial fractions. So the first one, so we'll have x squared plus 1 and x squared plus 1 squared, and then x squared plus 1 cube. And then this is you have to write a linear factor or a linear expression in the numerator. So we will have ex plus f, gx plus I, or plus h, doesn't matter, and ix plus j. So this is the partial fraction decomposition. Okay, and we have another example. Okay, I will give you. I will just mention the idea of it. So I want to evaluate this integral, which is 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 all squared. So the first step is to check the degrees. So the degree here is 3, and the degree here is, this x squared will be squared, so it will be power 4 times x, so the degree is 5. So here we can apply the partial fraction method. So you have to rewrite this expression, which is 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared, as you have to write its decomposition using the partial fractions. So x is not repeated, so it will be a over x, and here you will have x squared plus 1 plus another partial fraction over x squared with denominator x squared plus 1 squared. So here you will have px plus c, and here you will have dx plus e. And actually here you have 2 methods again, as usual, to calculate e and b and c and d and e. Actually, this is the first method here, which is comparing the coefficients, much easier, okay, than the other one. I'm not going to solve it, so but I will just give you the answer of A and B and C and D and E. So A will be 1, and B is -1, and C is -1, and D is 1, and E is 0. Okay, so let's substitute. So A is 1, so we will have here A, this is 1, and B is -1, so this is negative, and C also is -1, so this is -1, and D is 1, okay, and E is 0, so here you have just X. And then you want to integrate this one, which is also easy. So if you want to integrate this one, so you integrate this with respect to X, so you have to integrate 1 over X, which is easy, and then you have to integrate this one, which is not hard, and you have to integrate this one also, which is easy. Our integral is reduced to these integrals. So the first one is easy. So the first one is just ln x, ln absolute value of x, and the second one also we can multiply by 2.5 just to make the numerator to be the differentiation of the denominator. So you will have like -12 ln the absolute value of x squared plus 1 minus this integral, which is tan inverse x, plus the last one here. If you use this substitution, which is u equal x squared plus 1, so it's easy to find that this integral will be x squared plus 1 all to the power -1 over -1 plus constant. Okay, and in this way we saw an example on the last case, our last example for today. Okay, so example. If you have something like that, if you want to integrate square root of x plus 4 over x with respect to x. Actually, this is not a rational function, okay? But if you use this substitution, which is u equal u squared equal x plus 4, which means that u equals square root of x plus 4. So here you will have du equals dx. So our integral will be square root of x plus 4, which is u over x, which is u squared minus 4 times dx, which is 2u du. So it will be 2 times u squared over u squared minus 4 with respect to u, which is now, okay, now a rational function. So easily we can solve it as before. So this is okay. Now the degree of the numerator is the same as the degree of the denominator. So we have to apply the long division, or simply you can just subtract 4 and add 4. So if you do that, so I will be 2 times 1, because u squared minus 4 over u squared minus 4 is 1, plus 4 times 1 over u squared minus 4 with respect to u, and then you can solve it easily. So the first one would be 2 times the integration of 1 with respect to x plus 2 times 4, which is 8, the integration of 1 over u squared minus 4 with respect to u, which is easy using the partial fraction or fraction method. Or even I think you can use, this could be, I think, the arctange of u over 1 over of u over 2. Okay, so anyway, so here using an appropriate substitution, which is u equals square root of u of x plus 4. So we could convert this non-rational function into a rational function. Okay, and then we could calculate the integration. In general, if the integrand contains something like that, the nth root of a certain function, so maybe you could use this substitution such that you convert the the non-rational function into rational function, and then you could integrate it as we have seen. Okay, so now we're done with the partial fractions method. Thank you.